So we will discuss further some more details about that BH curve or hysteresis curve. First of all, we will discuss about this BH curve, then we will go further. Next. Okay, so this is the hysteresis curve. We can also call it as BH curve. Okay, otherwise we can also call it as IH curve or MH curve. That means in the x-axis, we will take H. H means applied field. Applied field. Okay, simply magnetic field intensity. Magnetic field intensity. In y-axis, what we will take here? So in y-axis we will take B. Okay, R, sorry, I. So I means intensity of magnetic field. B means induced magnetic field or magnetic flux. Or M. M is the magnetization. So we'll take any one of these three parameters. So either B or I or M. So whatever you will take, so that shape of the curve will be like this only. Shape of the curve. Actually, it will be, so after will become, it will be saturated. So it will be like this. Okay, while drawing in your notebook, so draw like this. So after particular point, it will become saturated. Okay, so this is the, so BH curve here. I will explain you step by step. So in last class, I already explained you how it will be. So once again, I will explain. So now, so if you apply the magnetic field, so take a one bar magnet here. So either its shape will be, so bar magnet means it will be rectangular. Okay, you can take any type of magnet. You can take any type of magnet. Now we will apply the magnetic field. So this is the especially, so different types of materials. So this hysteresis curve will be different. Hysteresis curve will be different. Mainly that hysteresis curve we will discuss in ferromagnetic materials. Ferromagnetic materials. So if you apply the magnetic field, if you apply the magnetic field, what happened here? So with at initially, so without applying any magnetic field, so that means, so this is examples for ferromagnetic materials are ferrous, cobalt, nickel. So these are the best examples for ferromagnetic materials. Okay. And their alloys also, ferrous alloys or cobalt alloys, magnet alloys, sorry, ferrous, cobalt, nickel alloys. So these alloys also exhibit the ferromagnetism. Okay, so first of all, what happened if you without applying any magnetic field? So that means if you will take iron rod, so without applying any magnetic field, so due to that iron, is there any magnetic field? So that means, is it attract to any other particles? It does not attract. That means there is no induced magnetism inside the that ferrous, inside the that ferrous material. Okay, once if you apply the magnetic field, if you apply the magnetic field means we are applying magnetic field is H. So applying magnetic field is here. Wait a minute, why it's not coming? Yeah, so applied magnetic field is H here. Okay, we are applying H magnetic field. So if you apply the H magnetic field means what happened? So field lines, what is the meaning of H? Number of field lines per unit area in a vacuum, or air. Okay, number of field lines in a unit area in the vacuum or air. Okay, that is H. Okay, if you increase the H value, what happened? So number of field lines will be increases. If you increase the H value means number of field lines will be increases. Okay, now automatically what happened? So that field lines enter into the this magnetic material. Okay, so those, how whatever the magnetic field lines enter into the inside the magnetic material, so this material, so that number of field lines inside that material, okay, that is B, that is induced magnetic field. Okay, number of field lines per unit area. Otherwise, magnetization means how much area is magnetized. Okay, there are so many atoms will be there inside this material. Each atom will act as a one dipole. If you apply the external magnetic field, means what happen, those dipoles are magnetized. Okay, so because of that magnetization, what happened, those dipoles orient in a particular direction. That means each atom will act as a one dipole, but the resultant dipole momentum is zero without applying any external magnetic field, because different dipoles orient in a different direction. Different atoms will orient in a different direction. That's why resultant magnetic momentum is zero. So this concept we will read in the later. So different types of magnetic field will be there. So magnetic material will be there. In that we will discuss about this briefly. Each atom will act as a one dipole. So without applying any external field, what happened? Those atoms, those dipoles orient in a random direction. That's why resultant magnetic field is zero. Resultant magnetic field is zero here. Okay, now with increasing the applied magnetic field, we are increasing the magnetic field like this direction. So like this direction, if you increase the magnetic field like this direction, means what happened, so that induced magnetic inside this bar magnet, inside that bar magnet, so these atoms orient in a field direction. These atoms orient in a field direction. That's why magnetic field is developed inside this bar magnet also. That's why if you increase the H value, automatically that induced magnetic field is increases. Okay, so it will be increased up to particular value. After that it will become saturated. If you increase the H value, what happen, B value also increases, or I value also increases, M value also increases. Okay, so it will increase up to particular H value. So up to particular H value. After that, if you increase the H value also, applied magnetic field value also, that B value will become constant. What is the reason, means, so at a particular H value, all atoms orient in a field direction. All atoms, that means each atom will act as a dipole. That means all dipoles will orient in a field direction. So there are no further dipoles, okay, to orient the field direction. So that's why what happened here, it will become saturated. B value will become saturated. That intensity of magnetization or magnetic field induction also. So what happened, it will become saturated. Now, so what we are doing now, decrease the H value, decrease the applied magnetic field. What happened, so if you decreasing the applied magnetic field, that induced magnetic momentum inside this bar magnet is decreases. So after removing the H value also, now we are removing external magnetic field. Now, so we are removing this external magnetic field here. Right? Now we are removing this external magnetic field. What happened, so there are some induced magnetic field inside the bar magnet. So inside the bar magnet, so what is the reason, means, so due to the external magnetic field, that bar magnet is induced. So that's why it is magnetized. That material is magnetized. After removing the external magnetic field also, it act as a one magnet. So that's why what happened, after removing the external magnetic field also, there are some residual magnetic field inside the bar magnet. Thus that residual magnetic field we will call it as retentivity. The value of B after becoming the H value is 0. So the value of B is called as retentivity. For hard magnetic materials, this retentivity value is high. For soft magnetic material, this retentivity is okay, small. Okay, now coming to the so now apply the magnetic field. Apply the magnet. So previously magnetic field direction is like this direction. Now we will apply the magnetic field like this direction. Like this direction. What happened? So inside these dipoles will be there. So those dipoles try to orient in a field direction. Try to orient in a field direction. That's why what happened? That magnetic field is decreases. That magnetic field is decreases. So with increasing the applied magnetic field in opposite direction, at a particular magnetic field, uh, particular h value, particular applied magnetic field, that induced magnetic field will become zero. Induced magnetic field will become zero. That means that B value will become zero. That applied magnetic field we will call it as coercivity, at which opposite applied magnetic field, that induced magnetic field will become zero. So that H value we will call it as coercivity. Okay, so this is the definition of coercivity. Now if you increase the further h, value, what happened here? So this b value increases and reaches to the maximum value. So and reaches to the maximum value. After that, if you increase the h value also, so b value does not increases. That means it will become saturated. Okay, if you increase the h value also, b value will become constant. Okay, this is the saturation in opposite direction, because so all dipoles orient in a, so like this. Now this direction, field direction, now field is so this side. Okay, so that's why opposite side of the previous applied. Okay, now again we will decrease, so reduce the applied field, now field direction. So that b value, will be decreases like this manner, not this manner. Okay, so like this manner. After removing the h also, there is a some induced magnetic field. That value is called as retentivity. That value is called, after becoming h equals 0 also, there is a induced magnetic field, that is called as retentivity. So now if you increase the h value in opposite direction, at a particular h value, what happened here? So this b value will become 0. If you increase the h value again, so that b value is increased like this manner, and after that it will become saturated. Okay, so this is the bh curve. Or hysteresis curve. So mainly you have to remember the what is the retentivity, what is the coercivity. Initially, what is the direction of, so b, so according to the h, if you increase the h value, initially b value increases like this manner, after that if you decrease, so it will become saturated, b will become saturated. After that, if you reduce the h value also, what happened? That b value is decreases in this direction, not original direction. So original direction is oa, but so now it is decreasing in the direction of a to b, ab, and at a particular point, so what happened? So if h value will become 0 also, so that that b value does not 0, that b value will call it as retentivity. What is the residual magnetic field inside the bar magnet? That residual magnetic field we will call it as retentivity. Now apply the h value in opposite direction. So now that b value will decreases in the direction of, so like this, b to c, direction. Okay, at a particular value, what happened? So this b will become 0 at a particular h value. The induced magnetic field inside the magnet will become 0. So that that h value will call it as coercivity. Now further increase the h value. What happened? B value is increases in the direction of c to d. After that, it will become saturated. If you increase the h value also, b value will become constant. Now decrease the So decrease the H value. If you decrease the H value also, so what happened? B value will decrease in the direction of D to E, not so previous direction. So it will decreases in the direction of D to E. Okay. So at a particular, so if you after that what happened? If you make the H value 0 also, there is a some induced dipole momentum inside the magnet, that is called as retentivity. Okay, now further, now increase the H value in opposite direction. Okay, at a particular H value, what happened? So that residual magnetic field will become 0. That means induced magnetic field will become 0. So that at which value, at which H value, applied magnetic value, uh, it B value will become 0. That H value we will call it as coercivity. Okay, so now if you further increase the H value, this will be increased in the manner of F to A. Okay, so this is the hysteresis curve. So you have to explain the each point: O to A to B, B to C, and C to D, and D to E to F, and F to A. So this is a repeated curve. So repeated curve. So this curve we will call it as hysteresis curve. Okay. Now coming to the about the total so discussion, whatever we discussed. So that path A B C D E F A as hysteresis loop. Okay, so this is a closed curve. So this is a closed curve in HI plane or the HB plane or HI plane. So I means instead of B we can take I also, we can take M also. Okay, so whatever you can take. So if they ask in particularly HI curve means instead of you wrote instead of B you wrote I. Okay, otherwise MH curve or HM curve. Okay, you can write instead of I you can write M. So otherwise BH curve. So BH curve means instead of I you wrote B. Okay, so remember here, so three parameters, for three parameters also curve will be same, curve will be same. Okay, now coming to the so classification of magnetic materials. Classification of magnetic materials. So the classification here, there are several types of magnetic materials are there: paramagnetic materials, diamagnetic materials, ferromagnetic materials. Okay, so these are the different types of magnetic materials. So for some more also there, antiferro and ferri. Okay, antiferromagnetic materials, ferrimagnetic materials also. Okay, so different types of magnetic materials are there. So we'll discuss those magnetic materials. Now coming to the, so these are the classification of magnetic materials here. So diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, ferrimagnetic. Okay, so now first of all we will discuss about the diamagnetic material. In the absence of applied magnetic field, each atom has net zero magnetic dipole moment. Okay, so without applying any magnetic field, without applying any magnetic field, what happened? Each atom previously what we discussed. So in case of ferromagnetic material, each atom will exhibit the some dipole momentum. So magnetic dipole, each atom will act as a magnetic dipole, there is a resultant dipole momentum. But in case of diamagnetic materials, so each atom will act as a one dipole, but result, so atom having that dipole momentum of the atom is zero. Atom dipole momentum of the atom is zero. Okay, these type of magnetic materials we will call it as diamagnetic materials. Okay, in the presence of applied magnetic field, the angular velocity of electronic orbits are changed. So these induced magnetic dipole moment uh, themselves opposite in the applied field. Okay, so now what happened here? So I will explain you through PDF here. Okay, so Yeah, so that means if you will discuss along the atomic state means without applying any external magnetic field, so resultant magnetic dipole momentum of the diamagnetic material is zero. Okay, now after applying the magnetic field direction, after applying the magnetic field direction means, suppose if you apply the magnetic field like this direction means, so that dipole momentum will become in opposite direction. That linear momentum of the electron, linear orbital momentum of the electron will become so oppositely, so opposite direction. So that linear momentum will become so oppositely, it will be so linear momentum will become opposite direction, its direction will be. So that's why what happened, that dipole momentum will be like this, opposite direction of the applied magnetic field. Okay, that means each atom will become a opposite magnetic dipole momentum. So if you will take resultant magnetic momentum is so opposite direction of the applied magnetic field. Okay, the substance. So if you will take substance means bar magnet means bulk magnet, not in atomic level. If you will take this substance placed in a magnetic field, so that feeble magnetization in opposite direction, it will be magnetized, but so that magnetization is in opposite direction, not to the field direction, not to the field direction. So this mechanism will call it as, this type of material will call it as diamagnetic substances. Okay, so which materials magnetized in opposite direction to the field direction. So those type of materials we will call it as diamagnetic substances. Examples are bismuth, zinc, copper, Ag, Au, NaCl, H2O, Hg, H2. So these are the some examples for diamagnetic materials. And yeah, uh, so these induced magnetic dipole moments align themselves opposite to the applied field. Okay, that's why resultant magnetic field will be so opposite direction of the applied magnetic field. Okay, now this susceptibility and permeability. So relative permeability is susceptibility is less than 0 and relative permeability is less than 1. So what is the susceptibility formula? Susceptibility chi is equal to, okay, mu is equal to permeability, mu is equal to so B by H. So permeability mu is equal to, so permeability mu is equal to B by H. Okay, so B by H here. Now, so what is the H means? H means applied magnetic field. So applied magnetic field means H will be like this direction. Okay, now B is induced magnetic field inside the material. Induced magnetic field. What is the direction of induced magnetic field? Like this direction. Induced magnetic field is like this direction. That means both are opposite direction. That's why what happened? Mu value will become mu value. So it will become negative. Okay, so that's why mu is less than, see here it is given here. Yeah, so chi value will become less than 0, so mu value will become less than 1, less than 1, because b value is less compared to the h value, b value is less compared to the h value. That's why what happened, mu value will become automatically less than 1. Okay, less than 1. Now coming to the, so what is the chi is equal to I by h. So I means induced magnet, induced magnetic field. So that intensity of magnetic field, that is in opposite direction. I by h value will become so less than 0, less than 0. So that chi value will become less than 0, so mu value will become less than 1. Okay, now usually diamagnet is very small effect in natural materials, that is, so mu r is approximately 1. Diamagnetism can be big effect in superconductors and in artificial magnets. So if you will take natural magnetic materials, so that means diamagnetism is very small. If you will take artificial magnets, so it we will prepare so more diamagnetic material, as well as superconductors also. So its diamagnetism is very high. Okay, diamagnetic materials are repelled from the either pole of a magnet. Okay, see here. This is the, so now what we are doing here, without applying, so with, so this is a superconducting material. Superconducting material, so T greater than Tc, that means at a critical temperature, at a critical temperature what happened, so that magnetic material will become, so diamagnetic material. So here before T greater than Tc, so these superconducting material will act as a paramagnet. So if T less than Tc, T less than Tc, so this superconductor will exhibits a diamagnetism. So that's why what happened here, so that magnetic field lines are repelled by the this diamagnet, repelled by the this diamagnet. That's why what happened here, so at a particular temperature, at a particular temperature, so the temperature is, we will call it as critical temperature. So the temperature is greater than critical temperature, this superconductor will act as a ferromagnet. So less than critical temperature, this superconductor will act as a diamagnet. Okay, so this is, so we'll discuss about the superconductor so later, so no need that much of here. First of all, we'll discuss about the these diamagnetic materials, for properties of the diamagnetic material. Now first property, when a bar of a diamagnetic substance is suspended freely between the two magnetic poles, then the axis of the bar becomes perpendicular to the magnetic field. See here, so we are taking, so this is a very high magnets. So due to that high magnets, what happened, some magnetic field is produced. So now let us place a diamagnetic material in between the bar magnets, in between the this magnetic field. Okay, what happened, that bar magnet will become, so that axis of the bar magnet means this one, this is the axis, that axis will become perpendicular to the magnetic field, perpendicular to the magnetic field. And so these magnetic field lines also, these are actually, so that magnetic field lines are like this, like a without, if there is no bar magnet, there is no bar magnet means that magnetic field lines will become like that. If you place the bar magnet, what happened, that magnetic field lines are repelled by the, so that diamagnetic material. That's why what happened, so previously if you will take this position, this, see here, if you will take this position, wait a minute, yeah, if you will take this position, what happened, so number of field lines per unit area, number of field lines per unit area is high. If you will take inside the material, number of field lines per unit area is less, because see here, so that bar magnet repels the magnetic field lines, that's why, so it will enter into the bar magnet, but so it will away, so it will repel by the bar magnet, that's why. So if you will take certain area, number of field lines will be decreases. That means B value will be decreases. B value will be decreases means, so mu is equal to B by H. Mu equal to B by H. That's why, so B value is less than 1. Less than 1. Now coming to the second point. See the permeability. So the permeability mu is equal to B by H. That's why B value is less than, so less than H value. That's why B by H value is less than 1. Now coming to the susceptibility. Susceptibility means here, so this will be magnetized in opposite direction. So it will be, diamagnet will be magnetized in opposite direction. That's why here susceptibility value will become less than 0. Less than 0. Less than 0 means that susceptibility is negative. Okay, next point. So if you will take a diamagnet liquid, if you will take a diamagnetic liquid in a u-shaped one tube, so we will take the one tube, the tube will be u-shaped tube. If you place the diamagnetic liquid on that. So if you bring the electromagnet nearer to the that diamagnet liquid, what happened? So automatically this level will be reduces. This level will be reduces because if you place the magnetic material, if you place the if you place the magnetic material here, so what happened? So before its level will be, I will change the color here. Okay, its color is not changing, I think. Okay, so before what happened, it will be uh, see here. Okay, so before this level will be up to here. After placing the bar magnet, this level will be decreases. This level will be decreases. That means this side level will be increases. Okay, another side there is no bar magnet. There is no magnetic field applying in this direction. That's why what happened? So that liquid level will be decreases from here to here. Without bar magnet, what happened? Liquid level will be, both liquid level will be equal. So this tube liquid levels will be equal after applying the magnetic field one side. What happened? This side liquid level will be decreases. This side liquid level will be increases. This side liquid level will be increases. Okay, so what this is due to the that magnetic field. So diamagnet is the induce the opposite direction of the applied magnetic field. So because of the, so this opposite in the induced magnetic field, what happened? Its level will be decreases. Its diamagnetic liquid level will be decreases. Okay. Now coming to the next point. Diamagnetic substance is placed in a non-uniform field. Non-uniform field means one side we will apply the very high magnetic field. Yeah. One side we will apply the very high magnetic field, another side we will apply the low magnetic field. Non-uniform magnetic field means one side we will apply the high magnetic field, and the other side we will apply the low magnetic field. Means the diamagnetic material so moves towards to the lower magnetic field direction. Lower magnetic field direction. Okay, so if you place the diamagnetic in a non-uniform magnetic field, so that diamagnetic material moves towards to the lower magnetic field direction. Okay, now coming to the, so this is about the diamagnetic material. So next one is the paramagnetic material. Okay, paramagnetic material. So the substance which when be placed in a magnetic field acquire a feeble magnetism. Okay, in the direction of magnetic field are known as paramagnetic substances. Okay, now same case if you apply the, so if this is the magnetic field here, if you place the diamagnet, if you place the diamagnetic material, what happen? Yeah, so we are placing diamagnetic material that field direction. So magnetic field direction will be like this. Okay, now what happened? This magnetic field lines, so like this, bend towards to the this magnet. So if you will take, so this magnetic field line actually crossing like this, but it will bend towards to the this paramagnet. Okay, that paramagnet, that bending also very small, that bending also very small, because feeble magnetism, very less magnetism will be produces, less magnetism will be produces. Okay, so that type of magnetic material we will call it as paramagnetic substances. Examples of paramagnetic materials are aluminum, platinum, Mn, CuCl2, O2. So and solutions of the salts of, okay, iron salt solutions. Iron salt solutions are also examples for paramagnetic material. Now properties. See here. So this is the diagram here. So when a bar magnetic substance is placed in a magnetic field, it tries to concentrate the lines of force into So in that material, that means if you will take number of lines per unit volume, that is the, what is that? That is H value. Okay. Now here number of lines per unit unit area, not volume. So the number of lines per unit area inside the material, that is the B. Okay, if you will take B by H, B by H is greater than 1, because so here inside the bar magnet number of field lines are more, that means number of field lines per unit area is more. Okay, that's why B by H is so greater than 1, that's why mu value is greater than 1. See here, that magnetic induction B is slightly greater than the applied field H. Therefore, mu value will greater than the 1. Okay, now susceptibility. Susceptibility means here, so magnetization. So that magnetization will become, it is positively magnetized. So positively magnetized. That magnetized, positively magnetized. That's why. So chi value will become positive. So chi value will become positive. Okay, and so it is greater than 0. Positive is nothing but greater than 0. So mu value will become greater than 1. Okay, now coming to the when a bar magnet, paramagnetic material substance is freely suspended between the magnetic poles. What happened? So its axis becomes parallel to the magnetic field. Moreover, the poles produced at the ends of the bar, one, yeah, see here. So this is the bar magnet. This bar magnet is suspended inside the magnetic field. What happened here? That bar magnet will become parallel to the magnetic field direction. Yeah, that axis of the bar magnet, this only center of the center line, whatever the drawn at the center line, that is the axis of the bar magnet. That axis of the bar magnet is parallel to the field direction, parallel to the field direction in case of paramagnetic material. But in case of diamagnetic material, that magnet will be oriented like this. Okay, oriented like this manner. That axis will be perpendicular to the applied field direction. Axis of the bar magnet will be perpendicular to the applied field direction. And if you place the non-uniform magnetic field, if you place the bar magnet in a non-uniform magnetic field, what happens? That paramagnetic substance attract towards to the stronger magnetic field. So which side? So magnetism is high. So like that direction, it will be attract towards the so stronger magnetic field direction. Okay, this is about the paramagnetic materials. Paramagnetic materials. In next class, we will discuss about the ferromagnetic substances. Ferromagnetic substances. Okay. Yeah, if you have any doubts, means you can ask. Now I am taking the attendance. Yeah, if you have any doubts, you can ask. Otherwise, you can leave from the session.
Sir, can you give us important questions for mid and sem exams?
Important questions.
Yes, sir.
So
This
first,
amount of time.
yeah. First
So,
3 units you have to read completely. Okay, all questions. So because paper we will not, so our college will not prepare the paper. So that's why. So first 3 units, from each unit you will get 2 questions. So first 3 units, each unit you will get a 14 marks question. 14 marks question means may contain, that 14 marks question may contain A and B bits. Okay, that's why each chapter you will get approximately 4 questions. 4 questions means each question contains 7 marks. Okay, each question having so A bit and B bit. So that's why, so in each unit you will get first 3 units you will get two questions. Two questions means in first question A bit and second question B bit, like that. So total 4 questions will come on each unit. That's why we have to read so total 3 units perfectly. Okay, so I will give important questions for fourth unit and fifth unit. So because only fourth unit and fifth unit only one question will come. Okay, if you read perfectly 3 units means you can attempt all questions. all questions. So in case if you feel any difficult means you can choose so fourth unit and fifth unit. Okay, fourth unit and fifth unit. So in that fourth unit, fifth unit, I will give the important questions. Already I told the important questions about the fourth unit in previous class or day before class. Okay, so fifth unit I will give. Okay, fourth unit, fifth unit, again I will give the important questions. So first 3 units you have to read all questions. All questions. That's all. Any other doubts?